Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show CFD aerodynamic analysis of vehicles and also its parametric study using SolidWorks Pro solution. This analysis is a little bit different compared to previous analysis because before, while performing this parametric study, we have considered the input variables from the boundary conditions itself, but in this case we will consider input variables as the dimensions or the geometry of the object. In this analysis, initially we will perform the CFD aerodynamic analysis of the simple vehicle, and we'll see what are the different values of drag force, coefficient of drag, lift force, etc. By seeing the dynamics of flow particles, we'll have some kind of idea that what to be incorporated or what to be changes to be made to improve the coefficient of drag of this vehicle, right? In our first analysis, we are not doing any changes. With the normal design itself, we'll see the values of our coefficient of drag and also drag force, lift force, etc. And by seeing the results from this one, we'll see what are the changes required to improve the coefficient of drag of this vehicle, right? So without wasting time, let us start our analysis. We have already done the analysis, so no need of moving inside the setup. We'll show what we have done already, and that can be done from here itself. First of all, flow simulation environment was initiated from here itself. Started with the wizard and from general settings. Consider this one as external analysis and excluded cavities with the flow conditions and excluded internal space. We considered gravity in our case, and the direction of gravity is y. Next to that, default wall thermal conditions and roughness we considered, and finally ambient conditions. We have considered temperature as 20 degrees centigrade, though temperature is not that much of important in this case, and pressure was 10135 Pascal. And the most important part in this analysis is the velocity of the vehicle. So you can see that the vehicle was moving in x direction, so air will be moving opposite to x. So we have considered velocity of air equal to minus 10 meter per second. That is in the opposite direction of the vehicle. It is moving with a velocity of 10 meter per second. Okay, and also the coordinate system, it will be x because the vehicle is moving in x direction. So consider the coordinate system also x. With this one, we completed the initial setup. Next to that, we consider some kind of goals. What were the goals? You can see here. We consider 5 different goals. First goal is average total pressure. Second one is average velocity. And third one is drag force. Drag force and lift force is very important in this case. You know already. Drag force is the force which is opposing the velocity of the vehicle. So more the drag force, it will reduce the velocity of the vehicle. So our aim should be to reduce the drag force. By the same time, lift force. Lift force is trying to move the vehicle in the upward direction. Again, this lift force should be also as small as possible, because if the lift force is high, in this case, there will be less contact in between the ground and the wheel, so which is not expected. And finally, CD, that is coefficient of drag, right? It is actually a very important parameter. And normally, in case of all vehicles, this coefficient of drag varies in between 0.3 to 0.7. But in case of high moving sports vehicles, the value is actually approximately equal to 1. Right? So in our analysis, we will expect it will be in the range of 0.3 to 0.7. Let's see what happens in this analysis. As we have already run this simulation, so we'll directly move into the results and see the results one by one. First of all, we're going to see cut plots from front plane. Insert cut plots. And we want to see velocity. Let us see that one. It will be better to see from specific planes. You can see the car is moving in the x direction, and this is the profile at the back side of this vehicle. You can see it. Better to see in the form of an animation. Let us play it. You can see at the front side some kind of balloon is created. That means when there is a direct collision of air particles with the bus, velocity of the air particles reduces, and at the top side you can see some kind of increase in velocity, which is indicated by red color. And at the back side you can see blue zone, that means it is in the range of 0 to 1.339 meter per second. and you can see this strand is widely spread at the backside. So from these cut plots, it is not completely understood that what changes to be incorporated. That can be viewed from the dynamics of flow particles in a better way, right? Now next to that, we want to see pressure distribution through the same plane. So instead of velocity, let's change it to pressure. So we cannot see that much of changes in pressure. Only at the front side, when there is a direct collision of air particles with the bus, pressure definitely increases, and in other places you can see pressure is almost constant. So at the front side, pressure is the yellow zone, which is more, and top side also you can see a little bit of decrease in pressure, but almost all other places pressure is constant. So pressure is not varying that much in all cases, excluding the front bus when there is a direct collision of the air particles with the bus, right? So let us clear this one also. You can see it from different planes, right? Let us see it from other plane also. So cut plot to edit definition, and we'll see from right plane. Let us change the plane from here itself. This is the right plane, YZ plane. Okay, see. Let us view it in the form of an animation, right? Pressure, that much of changes is not there. Let us change it to velocity. We'll see velocity distribution, right? This is velocity distribution from right plane. It is symmetric both ways. So it is the same representation what we saw from front plane, right? Let us clear and hide this one. Cut plot 2, clear and hide. Next one is very important thing. That means we want to see dynamics of flow particles. That means how the air particles will be moving. So flow trajectories insert. Initially we will see is flow particles in the form of rectangles, and let us increase the numbers of 20 as 200 numbers. Let us see it. You can see here some kind of vortex is created at the backside, right? Now this vortex is not expected in aerodynamic analysis, and this one can be reduced by providing some kind of design changes or incorporating something at the backside, right? In CFD aerodynamic analysis, this is a very important one. By seeing the flow patterns of these air particles, we need to change the design, right? So let us see what are the different results we are getting, and based on that we need to change this vortex, and that can be done by different things. Initially in our previous analysis, we have changed the input variables or the boundary conditions to improve the performance of the vehicles or to optimize the design. But today in our case, we will not do that one. Instead of changing the boundary conditions, we will change the design itself, right? Let's clear hide this one, and we'll see this one in a different way, right? So a single plane will see it. Flow trajectories, clear and hide. Again, flow trajectories, edit definition. Instead of showing this one in the form of rectangle, we'll see in the form of a line only. Okay, right. So let us play. This is along a single plane, right? You can see at the back side, this vortex motion is created. This is clearly evident. This is a nice picture indicating all the changes to be incorporated that is visible here itself. So this is the point of attraction. We need to focus on this part only, right? See here, vortex is unexpected, and that needs to be changed by incorporating some changes in this design. Okay, let us play this one. You see the vortex motion is created and it is circulating at the back side. That needs to be changed by changing the design. Okay, right. So let us clear hide this one, right? So goal plots, insert, and we want to see all the results. So let us export to Excel. First one is CD, that means coefficient of drag. can see here itself, it is clearly visible that after 67 numbers of iterations, it is 0.734, right? Next one, you can see lift force. Lift force also is not that much. You can see after 67 numbers of iterations, it is 0.109. It is very less, which is good enough. Higher lift force is not expected. Higher lift force means it will be having less contact in between the ground and the wheels, which is not expected, right? Now the second one is the drag force. Drag force, you can see here it is, how much it is. It is 0.45 Newton. It is also very less, not that much. The average velocity of air particles, you can see after 67 numbers of iterations, average velocity of air particles is 8.99 meter per second. And initial velocity was actually 10 meter per second. There is reduction of air velocity. And finally, you can see average total pressure. We cannot see that much of changes in average total pressure. It is approximately equal to atmospheric pressure, right? So let us close this one. Next to that, what we will do is, based on the dynamics of flow particles patterns, we need to provide some kind of changes in this design to improve the performance of these vehicles or to decrease the coefficient of drag also, right? So without further delay, let us move into the second analysis. This is the second analysis. In second analysis, we provided some kind of extra attachment at the back side. At this point, it is hidden. Let us make it visible. Here, we provided this extra attachment to improve the dynamics of flow particles or to improve the performance of the vehicles. So let us move on to the results directly. First of all, we see the cut plots. So insert cut plots, and you want to see this pressure and velocity distribution through front plane together with contours, isolines, and streamlines. Let us see that one. This is velocity distribution. So vortex motion is actually not there, but still there is some kind of scope of improvement. Okay, you can see here the circular vortex motion is not there, but still there is some scope of further improvement that can be done by doing some kind of other changes also. That one will show later on. Right, this is the distribution of velocity throughout front plane. Okay, we can play this one. Let us play it. Let us clear and hide this one. So calculate 3, clear and hide. Next to that, we will see the most important part, that is your flow trajectories or dynamics of flow particles. Flow particles insert, and we will see from front plane, and instead of 20 numbers, we make it 200 numbers. Go and check. Let us see this one. So backside, you can see that vortex motion is not there. Still, there is some kind of improvement. So it should not be in this pattern. It should be in the same direction. There should not be any deviation of these flow particles. Right? You can play this one. You can see that vortex motion is not there at the backside, right? But at the top side, little bit of vortex is there. But backside, it is completely eliminated. Now, what we'll do is we'll see this one along a specific plane. So flow trajectories, clear and hide, and we'll see this one along a specific plane for better visualization of this one, right? So edit definition, and we'll see this one along a specific line, right? So let us play this. So this is the actual pattern. You can see vortex motion is not there at the back side, but still there is some kind of scope for improvement. You can see it clearly. At this side, velocity is very less, definitely, but here some kind of deviation of flow pattern is occurring that needs to be changed in a different design. But in our case, here by incorporating this attachment at the backside, the vortex motion what was created before, that was reduced, and that effect we will see from the goal process itself by seeing the exact results, right? Okay, so let us clear and hide this one. And next to that, we will see our results from goal plots. Goal pods, insert. We want to see all the results. Select it and we can transfer it to Excel. Let us see the first one, that is coefficient of drag or CD. You can see after 71 numbers of iterations, it is 0.69. So it is reduced. Initially, without having any attachment, it was 0.73. Now, by providing some kind of attachment at the backside, we reduce that coefficient of drag to 0.69. Initially, it was 0.73. Right? Next one, see lift force. This lift force and drag force will not be having that much of effect. It will be reduced very little amount, of course. You can see here the lift force after 71 numbers of iterations. You can see lift force is 0.13 Newton. And the drag force, you can see here, after 71 numbers of iterations, the drag force is 0.428 Newton. Negative it is, that means it is opposite to the velocity of the vehicle. Next one is average velocity. We started with the velocity of 10 meter per second. You can see after 71 numbers of iterations, is 8.97 meter per second. And finally, average total pressure. So we cannot see that much of changes in average total pressure. It is approximately equal to atmospheric pressure. Right? Let us clear hand this one. So in this analysis, you could see that by incorporating this design at the backside, we could reduce the coefficient of drag of the vehicle to a certain amount. We could improve the performance of the vehicle by providing some kind of design change. Now still there is some kind of scope for improvement, and that can be done using some kind of changes in this design. So what can you do is, in this flap or the backside, we can change the angle of attack. That means we can change the shape of these things by putting some kind of chamfer at different locations, right? This was a very simple aerodynamic analysis of a vehicle. In this analysis, we have shown that by changing the design, how can we improve the performance of the vehicle? Performance means we can improve the coefficient of drag, and even drag force and pull force all can be improved by changing this design. Okay, so with this one, we'll conclude our today's analysis. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.